Okay guys, physics 1.1 to 1.5. Before we start, you guys should know all of this. Pressure law, Charles law, Boyle's law. Here, if there's no V, then the volume is constant. If there's no pressure, then the pressure is constant. If there's no temperature, then the temperature is constant. And also guys, by the way, in all of them, the mass is constant. Okay? In all of them, the mass is constant, which is the number of moles. Thermometric property is a property that you can use to measure temperature. This is like the other formulas in the quiz. PV equal nRT. And these two, they're so confusing. Well, I keep getting the question 15 wrong. And this one, you guys should also know it. Okay, let's go to the quiz. Which statement about the temperature and sensation of hotness are true? The sensation of hotness is a quantity that can be measured? No. A person experiences a sensation of coldness when heat flows into their hands. No, guys, look. When heat flows out of you, then you feel cold because you're releasing heat. When heat flows into you, then you feel the heat. You feel hot. So cold is when it's going out, hot is when it's going in. A person experiences a sensation of hotness when the heat flows into their hands. Yes. So the sense of hotness can be used to accurately measure temperature. No. Like if you feel hot, you can say, oh, it's like 35 degrees. It's not that accurate. Temperature is the degree of hotness of a body. Yes. Which of the following are hazards of calibrating a mercury thermometer? Toxic steam, no. Water vapor is not toxic. Extreme cold, no. Use the steam point and the ice point. The steam point, 100 degrees, yeah, it can be dangerous, but the ice point, like you can touch ice, you're fine. Fragile glassware, yeah, the glass can crack from the extreme heat. Toxic mercury, yeah, the mercury is dangerous, and the extreme heat. And the pressure law to be applicable on a fixed amount of gas, which of the following quantities must remain constant? The volume must remain constant. Also mass, but it's not an option here. And the absolute temperature and speed of molecules are the same thing, and temperature, they're all the same, but volume has to stay constant and mass. If the pressure of the gas is 1200 millimeters of mercury, then the new temperature of the gas to the nearest degree is, okay. Pressure law. P1 over T1 is P2. Why is it so laggy? P2 over T2. Okay, so P1 here is 800. T1 initially at negative 73 degrees Celsius, but it has to be in Kelvin. Negative 73 plus 273, so you can get it in Kelvin. 273. Okay, and then it's gonna equal, what is the final temperature? Final pressure? 1200. 1200 over X. Okay, guys, you put it on your calculator. Give me 2 seconds. 800 over negative 73 plus 273 equals 1200 over X. You get 300. X equals 300. But that's the temperature in Kelvin, and we need to convert it back to degrees Celsius. So you do minus 273. You're gonna get 27, I think. 300 minus 273. Yes, 27. Volume of a fixed amount of gas at a constant pressure. Yeah, that's a thermometric property. Volume of gases and liquids is a thermometric property because the liquid thermometer, like let's say the mercury one, the mercury expands, so it's like the length of it increases. So you see how much it increased. So you, the thermometric property you're measuring is the volume. Mass is not thermometric. Hardness of an egg, like if the egg, non-thermometric. Length of mercury in a tube, yeah, that's thermometric. Okay, guys, this they're calibrating the steam point. So they have heat at the bottom, and this it's boiling water. And this you could just use your eyes. It's steam at 100 degrees because it's above the boiling water. Steam, and it's the steam point. In order to plot a point 10 centimeters 0 degrees, the thermometer was placed in contact with melting ice. Let me explain to you guys why it's melting ice. Remember the graph we took, it's like this. So while it's melting for water, while it's melting it's at 0 degrees. And while it's boiling it's at 100 degrees. It goes flat while it's like melting or boiling. Okay, that's why you use while it's melting. Okay. In order to plot a point 10 centimeters 100 degrees Celsius, the thermometer was placed in contact with steam of boiling water. If the length of mercury in the thermometer is 22 centimeters, when in contact with a cup of tea, the temperature of the tea is... Okay, so you go to 22 centimeters, you go up, and you go to 60. By the way, guys, I can't even draw lines. Like, I need to buy the Pro. Okay, wait, let's see again. 22, 60. Yeah. The size of 1 degree on the thermometer. Okay, guys, so 100 degrees is 30 minus 10 is 20 centimeters, yeah? So that's gonna be equal to 1 degree over x centimeters. You do shift solve, you're gonna get x equals 0.2. And they want it in millimeters, so that's gonna be 2 millimeters. 2 millimeters. A fixed amount of gas is kept at a constant temperature 25 degrees Celsius throughout the experiment. The initial pressure of the gas is 1 atmosphere and its volume is 12 atmosphere. The pressure is then increased to 3 atmosphere. Okay. To the nearest Kelvin, okay, so 25 plus 273 is 298. 25 plus 273 298. Why is it so laggy? 298. To find the volume of the above gas, one needs to apply temperatures constant, so that's Boyle's law. Boyle's law. The final volume of the gas. Okay, so we use Boyle's law. 1 P1 V1 equals P2 V2. So P1 is 1, V1 is 12, P2 is 3, V2 is X. Shift solve, X equals 4. Okay guys, for Boyle's gas law to be applicable, so the same as the question before, temperature was constant and we use Boyle's law. So temperature and mass. Mass was constant for Boyle's, Church's and pressure law. If the volume of the gas is increased to 30 centimeters cubed at a constant pressure, as a constant temperature, its pressure becomes, okay guys, you can see they're inversely proportional. So this one was double, the other one would be half. But I still solve it. So P1 is 8, V1 is 15, P2 is X, V2 is 30. 8 times 15 is 120, and divided by 30 is, I don't know. But X is 4. A fixed amount of gas is initially at 27 degrees Celsius and a volume of 8 centimeters cubed. The pressure of the gas is kept constant, and its absolute temperature is halved. So the pressure is kept constant. That's I think Charles' law. Wait, let me check. Let me make sure. Yeah, Charles. Charles' law. The final volume of the gas is, okay, so we use Charles' law. Okay. So V1 over T1 equals V2 over T2. So V1 is 8 centimeters cubed. T1 is 27 plus 273. The temperature is halved. Oh, bro, we don't even need to solve it, because we're gonna need to change it to Kelvin, half the Kelvin. Okay, that's too much work. You can see this one's halved, and they're directly proportional, so the other one's gonna be doubled. It's gonna be also halved. I don't want to solve the whole thing. The initial pressure of a dilute gas is 8 atmosphere. The volume is 12 atmosphere. The volume is 12 centimeters cubed. Charles' law, so pressure and mass have to be constant. If the volume of the gas is increased to 18 centimeters cubed at a constant pressure, then the new temperature of the gas to the nearest integer. Okay, this one, it's, yeah, we'll have to solve it. Okay, so V1, so 12 over 27 plus 273, 273 equals 8. We can try it. 18 over x. X is gonna be 450 minus 273. 3 equals 177. A fixed amount of gas is sealed in a rigid container of volume 20 centimeters cubed. Initially, the gas is at negative 23 and 600 millimeters of mercury. It's then heated to 27 degrees Celsius. To find the final pressure of the gas, one needs to apply the pressure law, because volume is constant, because they said rigid cylinder. Okay, so P1 over T1, so 600 over negative 23 plus 273 equals x over 27 plus 273. Okay, and then you put it on your calc and you do shift solve and you get 720. This is so like boring. A fixed amount of gas of volume 20 centimeters cubed is initially at 7 degrees Celsius, 2.5 atmosphere. Okay, so this time we have to use the long one. P1 V1 over T1 is P2 V2 over T2. P1, okay guys, let's try to do it fast, okay? P1 2.5, V1 20 over T1 7 plus 273 equals, okay, so pressure is doubled, so it's going to be 5 times X over 147 plus 273. Put it on your calc, shift solve. X is going to equal 15. Okay guys, look, let me explain this one a bit. So temperature is directly proportional to kinetic energy. Yeah. So here you multiplied the temperature by 4. So 4 times the temperature equals 4 times the kinetic energy, right? But here they don't want the kinetic energy. They want the speed, so basically the velocity. So the kinetic energy formula, it's 1 over 2 mv squared, yeah? So the velocity, it's squared. So the kinetic energy is the velocity squared. So temperature, like, is directly proportional to velocity squared. That means the square root of the temperature is directly proportional to the velocity. So here you multiplied it by 4. So square root of 4, you're gonna get 2 times 1900. Okay, that's gonna give you the answer. But also let me show you how to do it. 1200 over 300, but square root it, yeah, equals the initial velocity, so 1900, or no, my bad, the final velocity, so it's gonna be x over 1900. Okay, so if you solve that on your calculator, let me just do it quickly. Square root of 1200 over 300 equals x over 1900. It gives you 3800, which is the answer. 800, which is the answer. So you guys can take a screenshot of this if you want. Okay. A fixed amount of gas is kept at temperature T. The average speed of the particles V and the kinetic energy E. The temperature of the gas is quadrupled. Okay, so this question is the exact same thing, because here you quadruple the temperature. So here, as we said, the kinetic energy is also gonna be quadrupled, and the average speed is gonna be the square root of 4, so 2b. Okay. Guys, this question now, I got it wrong like 3 times and I had to repeat the whole video. So you guys better like up my video, yeah? Okay. Let me use the formulas, I don't want to mess up again. So P equals VI. So first, we need to find P. Because then when we find P, we're going to put the P and the time to find Q. And then when we have Q, we're going to use the mass and the specific heat capacity to find the change in temperature. So first, let's find P. P is V times I. They already gave you V and they already gave you I. I is the current and V is the voltage, okay? So P equals V I, which means P equals 2 times 12, which means P is equal to 24. Okay guys, let's put that at the top and we'll use it later. P equals 24. Okay, now let's erase this and find Q. What's Q? Q is P times T. So Q is P times T. T time, not not T temperature. So P is 24 times the time they gave it to you is 300 seconds times 300. So wait, let me quickly do that on my calc. 24 times 300, that's 7,200. Okay, 7,200. So Q 7,200 equals 7,200. Let's just take this question slow so I don't mess it up. Now we use Q equals MC delta T to find delta T, because they want the rise in temperature, which is delta T. So Q 7,200 equals M mass in kilograms equals M, see the specific heat capacity they gave it you, times 3,800, 380, what equals, times X. So if you do this on your calculator, 7,200 equals 1 times 380 times X. Shift solve, you get 18.9. X equals 18.9, and they want it to the nearest integer, so the answer is 19. Okay, question 16. The boiling point of ethyl alcohol up to 2 significant figures. So you see where the boiling point is, like where it's flat, that's the boiling point. Also when it's flat, also it can be the melting point. But here the boiling point is at 75. Also guys, I can't even draw straight lines, like I need to buy the Epic Pen Pro. What is it to 75? The specific heat capacity of ethyl acid up to 2 significant figures. Guys, this question is a bit hard. So again, Q equals P times T. T is the time. So here P is 50. And the times the temperature is increasing. Well, I need the straight line because let me use a different color so it's gonna be a bit weird. It's at 340. From 0 to 340, that's when it's increasing. So 50 times 340 equals, let me put on my calculator, T times 340 is 17,000. 17,000. Okay, so now we have Q. Let's leave it up here. Q equals 17,000. Now we can erase this. Okay, now let's see what they want. Specific heat capacity. So they want C. So the formula to get C is going to be Q equals M C delta T. This time T temperature. Capital T is temperature, small t is time. I'm not sure if I did that in this. Oh yeah, I did that. Okay, so small t is time, capital T is temperature. Okay, so 17,000 equals M 0.1 kilograms times X C, the one we want to find, times delta T. So we use the same time, the same place we used for the time. So it's from here to here. So it's from 75 to 10. So that's 65. 65. Okay, now let me do it on my calculator. 1,700 equals 0.1 times X times 65. You get X equals 2,615. Okay, but then they want it in scientific notation, so it's gonna be 2.615 times 10 to the power of 3, and they want it to two significant figures. Let me just erase all this so you guys can see. They want it to two significant figures. Okay, so you're gonna keep it 2.6 times 10 to the power of 3. Whew. Finally done with the hard questions. Okay, let's fly through the rest. Okay, after the temperature in a room drops from 25 to 20 degrees, 50 grams of water vapor condenses into liquid. Given the specific heat of vaporization of water is 2,400 kilojoules per kilogram. The specific heat capacity of water is 4.2 kilojoules. Okay guys, this question, it looks hard, but it's not hard. Like, they're throwing all these numbers, but you don't need them. We're gonna use this formula. Q equals M times L. So they want Q equals M, so 50 M times L. L is the latent heat of vaporization. It can also be latent heat of fusion. It's the same formula for vaporization and fusion. L is 2,400. It's 2,400. So if you do 50 times 2,400 on your calculator times 2,400, you get 120,000. Okay, Q is 120,000, but they want it in kilojoules, so you divide by 1,000, you get 120. Okay, so this one, it's going up, so it's heating, and at the bottom it's a solid, in the middle it's a liquid. So this is going to be heating of a liquid, and also if it goes up after, this is going to be heating of a gas. From solid to liquid, that's melting, and here liquid, and it's going to be gas, so it's boiling. The maximum amount of water absorbed by the hair of a typical person after a shower. Okay, guys, this one you do 20%. The human hair can absorb 20% of its own mass in water. The mass of a hair of a typical person is about 0.8. So it's so easy. This one you just do 20%. What the hell is that? Need to go slow for this thing to like work. 20% times 0.8. You get 0.16, I think. Yeah, 0.16. 0.16. And then you multiply that by 2.2. So just says 0.16 times 2.2 megajoules, so it's gonna be times 10 to the power of 6. Let me do it on my calculator. 0.16 times 2.2 times 10 to the power. You're gonna get 352,000. It's gonna equal 352,000. Okay, but they want it in kilojoules, so you're gonna divide by 1,000. So the answer is gonna be 352. On the Celsius scale, the ice point is equal to 0 degrees. The steam point is 100 degrees. Both are defined for the atmospheric pressure of it's 1 atmosphere, which is 100 kilopascal. 1 atmosphere is 100 kilopascal, and these two are just these. Yeah. A sample of 70 grams of steel, specific heat capacity 385, heated from 20 to 80 degrees. The quantity of heat needed to raise the temperature of this sample is. So Q, again, Q equals M C delta T. Okay, so M, it has to be in kilograms, so it's gonna be 0.07, because you divide by 1,000, times C, 385, times delta T, so 80 minus 20. Pisses me off how when I try to write fast, it just like makes my handwriting unreadable. Okay, 0.07 times 385 times 80 minus 20. You get 1617. And they want it in kilojoules, so 1617 divided by 1,000. You get 1.617, and they just want it in two significant figures. They didn't say that, but the correct answer is 1.6. 1.6717 is also 1.6. That's good. The phase change of the sample occurs when it's flat. So from 2 seconds to 8 seconds. Boiling point of mercury is 357 degrees Celsius and its latent heat vaporization is 300 kilojoules. The energy needed to completely change a 0.15 kilogram sample of mercury from liquid. Okay, so this one, it's the same formula. Q equals ml. So they want Q. M is 0.15. L is 300 times 300 equals, give me 2 seconds, I'll do it on my calculator. 0.15 times 300, it's gonna be 45. 40. Which statement describing evaporation are correct? Evaporation doesn't occur at boiling point only. If you leave like a cup of water outside, it will evaporate. Like some water will evaporate. Like the water isn't boiling. Evaporation causes the temperature of a liquid to drop. Yes, it does, because the hot particle, the hot molecule that evaporated went out, so the temperature drops. Like, I don't know how to explain. Evaporation occurs at any temperature. Yes, evaporation causes the temperature of the liquid to rise, not cause drop. At boiling point, evaporation takes place anywhere within the liquid. Okay, guys, before boiling point, evaporation only occurs at the surface of the liquid. At boiling point, like when the water is boiling, it occurs anywhere. Okay, guys, see this question, I would explain it, but I don't understand. So, and also I tried to search up a video explaining this on YouTube, and it's not clear at all, and it doesn't look like this. Like this figure, I don't know what's going on. So I'll just memorize this one. It measures temperature. Y's are made of the same material. W and Y. Why? I don't know. Like I have no idea. You can maybe you can look at the figure and see like Y or Z looks different. It's like darker, so it's a different material. But I really have no idea why. But the temperature, yeah, it's just to measure temperature. What does X measure? It measures current. Like how it measures current and it measures temperature, I don't know. It's a bit confusing, so just memorize it. Or if you want to understand, just go read the book. Which statement correctly describes the thermocouple? They have low heat capacities and they have high precision. The energy required to raise the temperature of 1 kilogram of a substance by 1 degree is called specific heat capacity. The energy required to turn 1 kilogram of a substance from solid into a liquid. Okay, it's latent heat of fusion. It's not like latent heat of melting, because that's not a thing. For melting, it's fusion. And for also freezing, it's the latent heat of fusion. And for like evaporation and or boiling, I mean, for boiling and condensation, it's just molar heat of vaporization. It's not molar heat of condensation. These are the only two. Like the other ones, they're not called that. The name of the lower fixed point is the ice point. It's at 0 degrees. The lower fixed point the lower fixed point is reached by placing the thermometer in melting ice. Okay, now obviously the other side, they're gonna ask for the upper point, so it's gonna be the opposite. Steam point, 100, boiling water. Absolute temperature of 150 degrees Kelvin you do 150 plus 273, you're gonna get 423. So the answer is 423. Yes, did you get any mistakes? Okay, alhamdulillah. Okay, we're finally done with the first video.